In today's class, we are going to look at electric potential. But before we dive into that, let's look at electric potential difference. Electric potential difference, or you can call it voltage, is the amount of work done per unit charge to move a charge from one point to another. Let's quickly take a look at this point charge. This point charge is situated at a position 1, and we want to move it from position 1 to position 2. How do we do that? Then we move it slowly from position 1 to position 2. We have this point charge situated in this point. Now, this is the direction of motion. We have moved it from 1 to 2. Then the potential at this point 2 will now be V2 minus V1, which will be equal to the work done in moving this test charge from position 1 to position 2, which is the work done in moving the test charge from position 1 to position 2, then divided by the test charge. Now, looking at this, you see that work done is measured in joules, capital J, and the charge is measured in coulombs. That is to say that the unit of potential difference is joule per coulomb. You can also have it as the volts, capital V. Now, there is something I want to enlighten you on. Remember that you can as well move this test charge in this direction. You can as well move it in this direction. You can also move it in this direction. So, work done in moving this test charge from either of this direction does not depend on the path taken. And the reason is because it is electrostatic force. Electrostatic force is the force that exists between these point charges, and it is called a conservative force. And you can also see another conservative force as the gravitational force. So you see, gravitational force is also another type of conservative force. And the work done in a closed path, work done in a closed path, is always equal to 0. So work done in a closed path is equal to 0. I hope that is well taken. Okay, let's go ahead. Electric potential. Electric potential is denoted with V. And electric potential at a point is the work done by an electric field in bringing a unit positive charge from infinity to that point. Let's assume we have this positive test charge here. It is at position 2. And we brought it from position 1. That means look at the direction of the arrow. Shows that this test charge here in position 2 was moved slowly from position 1 to position 2. Now, recall that the electric potential at this 2 will now be V2 minus V1, which is equal to the work done in bringing this test charge from position 1 to position 2, which is the work done in bringing the test charge from position 1 to position 2 divided by the charge. I hope that is well understood. Okay. Now, but let's assume point 1 is at infinity. Let's now assume that this point 1 here is at infinity. We'll put a sign for infinity. Now, remember that potential, or remember that electric potential at infinity is equal to 0. That is, V at infinity is equal to 0. Is that understood now? Now, let's take this point charge from infinity to this point here. So what we have to do is we are going to replace V1 with V infinity, because this point 1 now, we are now assuming that it is at infinity, and we are bringing this test charge from infinity here to position 2. So is that going to be V2, that is the potential at 2, minus potential at infinity, will now be equal to the work done from infinity to 2 divided by the charge. Since you know that potential at infinity is equals to 0, so we will now be left with V2 is now equal to work done at infinity to 2 divided by the charge. So this becomes the electric potential. Remember, we said that electric potential at a point is the work done by an electric field in bringing a unit positive charge from infinity to that point. So the work done here, we are the work done from infinity to what? To the point 2. That is what? The electric potential. Okay. Now let's look at electric potential due to a point charge. Let's look at electric potential due to a point charge. Electric potential due to a point charge. Due to a point charge. Okay, let's assume we have a positive test charge here at this position. We call this point charge. We have this point charge at that point. And we also have this point here. We call it position P. Then we have another point that is an infinity point, an infinity. Now, let's take this, that the distance between this point charge to this position P is our R. Then, and the distance from the point charge, as you are bringing it from infinity, we can call it what? X. Now, let's look at electric potential at this point P. Electric potential at this point P, which is at a distance R from the point charge. Let us move the test charge from infinity. So we are trying to move this test charge Q here from infinity to point. We are moving it from infinity here to point P. Please look at the direction of the arrow. We are moving this test charge from infinity to point P. We are moving it from infinity to point P. So let's draw the arrow to get to point P. Good. To point P. Then the electric potential at P will be the work done divided by the test charge. Here we now have Vp, which is the electric potential at P, minus potential at infinity, which is going to give us the work done from infinity to what? To P, to position P, divided by the charge. Remember that this test charge here, you are bringing it from infinity to this point P. So as you are bringing, that means you are doing work from this infinity to bring it from infinity to what? To the point P. So that's why we have the work done from infinity to P, because you are bringing the test charge from infinity to what? To P. As you are doing that, you are doing work is done, then divided by the charge itself. So since you know and we are aware, but potential at infinity is equals to 0. Therefore, we now have potential at P to be equals to, because here this will cancel out to become 0. We now have potential at P to be work done from infinity to P divided by the charge. So we can call this equation 1. We can call that equation 1. I hope that is taken. Now, by Coulomb's law, there is going to be an electrostatic force between the point charge. There's going to be what? An electrostatic force between what? This point charge here. Remember that this test point charge, we brought it to this point. So there's going to be an electrostatic force between this point charge and this test charge, which is going to be what? A repulsive force in the direction of the test charge. So there's going to be an electrostatic force, which is going to move in this direction. So we can call this F1 in the direction of what? Of the test charge. Because they are like what? Charges. And the test charge is smaller than the point charge. Also, an external force, Fs or F external, which is equal to F1, we move in opposite direction to oppose the repulsive force. So we are going to have here a force called F external, which is going to be equal to this repulsive force, but they are going to be in opposite direction. Reason being that, remember that electrostatic force is acting in this direction. Then as you are doing the work in bringing this test charge from infinity to point P, there's going to be an external force that's going to be what? Opposing this repulsive force that is moving in this direction. So we call it the F external. They are going to be equal, but in opposite direction. So which is now going to be F external is going to be equal to F1. Then, and it is going to be equal to the Coulomb's law, which is Q, KQ, Q small over X squared. We are considering this, the distance, S squared. So we can call this equation 2. Then calculating the work done, which is force multiplied by the displacement. Force multiplied by the displacement, which can only be done when the force is constant. But in this case of the test charge, the force will vary according to the displacement. Because of the displacement, S squared is too small. We have to apply integration for the tiny displacement, you covered before you get to P, for the tiny displacement. So we are going to apply integration in doing that. So please let me clean up. Okay. Now remember that we have that W from infinity to P is not going to be equal to, we are going to do integration, it's going to be equal to F external multiplied by ds, the tiny displacement. Now, in bringing the test charge, work done in bringing the test charge from infinity to point P will be an integration of work done by external force multiplied by the tiny displacement ds. So we are going to take the limit of our integration from infinity to r. So is that going to be work done from infinity to p is going to be equal to integral, taking the integration from infinity to r, that is the distance from the point charge to the position P, is not going to be Fs, that is F external, multiplied by the tiny displacement. Now, this is going to be equal to integral from infinity to r. Our F external, remember we said it is what? K Q naught over S square multiplied by S. Remember that displacement is in positive X axis, while the external force is negative X axis. So the angle between them is going to be what? 180 degree. And cos 180 degree, cos 180 degree is going to be equals to -1. So cos 180 degree is going to be -1. So we rewrite the equation of work done as work done from infinity to P will now be equals to integral from infinity to R negative K capital Q small q over x squared dot ds. Okay, now let us bring the constant outside. Let us bring the constants outside. So the constants we are going to bring outside is kq q naught. So we bring this outside, kq small q naught. Then we go ahead and integrate the rest. That's from infinity to r. So what we now have is left is negative 1 over x squared dot ds, which is also going to be equal to then we can rewrite this following the law of indices. Is not going to be negative x raised to power negative 2 ds, then which is going to be equals to, we still do that, is not going to be negative x raised to power negative 1 over negative 1. Because of course you know that here you are going to add plus 1 based on our integration what rule. So you now have negative 1. So at the end of the day, we will now have it as x negative 1 infinity to r plus c plus c. So here is this will also be equal to 1 over x, that's from infinity to what, to r. Then we now have that our kq, bring up our constants, brackets 1 over x from infinity to r, which is equals to kq q naught. 1, we are going to replace our s with r, minus, we are going to replace our s2 with infinity. So remember that infinity is what? Is 0. So this is 0. We now have it as kq q naught over r. So this formula becomes the formula for work done by the external force. Work done by the external force. That is work done by, so this is equals to work done by external force. By the external force, which is W external. Okay, let us now try to substitute this equation in our equation 1. Remember our equation 1? So let's try to substitute that into our equation 1. So remember that our equation 1 is Vp, that's potential at P, is equals to work done from infinity to P over Q naught. So it's not going to be equals to K Q naught over R, then divided by Q naught. So which is now going to be equals to this Q naught here. We cancel this Q naught. So we now end up with K Q over R. So this now happens to be the formula for electric potential. The formula for what? Electric potential at a point P. So here Vp is now equals to this. This electric potential V at the point P. So you can now have it generally that V is equals to AQ over R. Okay, so let's quickly look at one or two examples. Find the work done. Find the work done in moving a 3 microcoulomb charge from A to B. From A to B. Find the work done in moving a positive 3 microcoulomb charge from A to B. Okay, let's look at that. Let's assume we have this charge. We have this charge here. We have this charge. This is positive 3 microcoulomb. And we are moving it from point A we have point A here, and we have point B here. So this is point B. And this distance here is 2 meters. And this distance here is 1 meter. And we have a test charge here, which is 2 microcoulomb. 2 microcoulomb. Now, as we are moving this charge from point, as we are moving this charge here, okay, sorry, this charge here will be 3 microcoulombs. Yeah, that is 3 microcoulombs. It's 3 microcoulombs. So as we can still change this so that we don't run into confusion. So let's have this as 5 microcoulombs so that to avoid confusion. So we are moving this test charge 3 microcoulombs from this point A to point B. So we are going to find the work done. We are going to do what? Find the work done. So remember, we are moving it from A to B. So the potential difference is going to be what? VB minus VA. Remember that. So we have to pay attention to the direction in which we are moving our charge. If we are moving from point B to point A, let me show you this. If we are moving from point B to point A, so it's going to be VA minus VB. That is the potential, the final potential minus the initial potential. But as we are moving it from A to B, it's not going to be what? VB minus VA. That is the final potential minus the initial potential. Is that understood? So here, let's clean this up. So we are looking at the potential from A to B. So it's going to be VB minus VA, which is going to be equals to the external work done, W external work, divided by the charge. So we are now looking at this work. So the work done will now be equals to potential difference multiplied by the charge, multiplied by the charge. So what we are going to do now is we are going to find potential at B and also potential at A. Okay, let's now look at potential at A first. So we look at potential at A, that is VA. Then VA is going to be what? It's going to be KQ over RA, which is equals to, our K is constant, Coulomb's constant, 9 times 10 raised to power 9, multiplied by the charge, multiplied by the charge. The charge is what? Is 5 microcoulombs. 5 microcoulombs. That is here, this charge to point A. So this is the direction. So it's going to be divided by 1, which is going to be, so it's going to be 9 times 10 raised to power 9 multiplied by 5 times 10 raised to power 6, negative 6, which will give us, here is going to be 9 times 10 raised to power 9 multiplied by 5 times 10 raised to power negative 6, because it is microcoulombs, divided by 1, will give us 45,000 volts. Okay, let's look at potential at B. It's also going to be KQ over RB, which is equal to 9 times 10 raised to power 9 multiplied by 5 times 10 raised to power negative 6, divided by, here we are going to have our distance because we are moving it from this point and we're looking at the B here. So it's not going to be 1 plus 2. So from this positive point charge here to this to point A is 1 meter, and from point A to point B is 2 meter. So we are moving it from this point all the way towards to B. So it's going to be 1 meter plus 2 meter, which is equals to what? 3 meters. So we have what? 3. So when we resolve, that, we are going to have okay, we are going to have 9 exponential 9 multiplied by 5 exponential negative 6 divided by 3. We are going to have 15,000 volts. We're going to have 15,000 volts. So here, let us now come to this place and continue. So here, our work is now going to be minus VB minus VA. So VB minus VA. So it's not going to be VB minus V. Okay, it's not going to be VB is 15,000 minus VB minus VA, which is 45,000. Then multiply by our charge. Multiply by our charge. Our charge is 3 times 10 raised to the power negative 6. So what are we going to have? We have 15,000 minus 45,000, then multiplied by 3 times 10 raised to the power negative 6. So we are going to have here is going to be we're going to have here 0.09, negative 0.09 joules. 0.09 joules. Okay, let's look at another one. How much work is required to move? How much work is required to move a 400 microcoulomb charge across a potential difference of 200 volts? So here we are looking at the work. How much work is what required? So, and we have our charge Q to be equals to 400 microcoulombs, which is 400 times 10 raised to the power negative 6 coulombs, and the potential difference which is change in V, is equals to 200 volts. So let's recall that potential difference is equals to work done per unit charge. So we are looking for the work, which is now going to be potential difference multiply by the charge. So which is equal to the potential difference here. We have it as, we have the potential difference as 200 multiplied by the charge. We have it as 400 times 10 raised to the power negative 6. Then which is equals to, we'll take that 400 exponential negative 6 multiplied by 200. We have that as 0.08 joules, because the SI unit of work is what? Is the joule. Okay, I hope that is well understood. Let's go ahead with example number 3. Find the potential, find the electric potential at the center of the square below. So let's have this, let's have this square. Let's have this square. So we have Q here, we have Q here, we have negative Q here, we have Q here, and here the distance here is A, distance here is A, and distance here is also A. So let's call this position 1, let's call this position 2, and let's call this position 3, and let's call this position 4. Now, and we are asked to find what? We are asked to find the electric potential at the center here. So we are looking at the electric potential at the center. So that means we have this, we complete this. We are looking at the electric potential at the center. We're looking at the electric potential at the center. So remember, this is at 90 degrees to this. So let's assume we have here distance here r. Distance here r, because they are equal, is a square. We have that here. And this is what? A right angle triangle. So we have to use Pythagoras theorem to find that. So here, remember, looking at this is a right angle triangle. This is a right angle triangle. This, see that, is a right angle triangle. So we are now going to have by Pythagoras r square. So this r square here, okay, plus this r square here is going to give us a square. So this is the hypotenuse, this is the opposite, and this is the adjacent. So we have it r square plus r square is going to give us a square. So r square plus r square will give us 2r square. It's going to give us a square. Then our r is not going to give us square root of a square divided by 2. So which is not going to give us a divided by root 2. A divided by root 2. So that is to say that this our distance here now, I call this a divided by root 2. is this. Also here is going to be also A divided by root. Now understood. Okay. Now let us also look at the potential. So total potential, the total electric potential here is going to be, the total electric potential here is going to be V1 plus V2 plus V3 plus V3. The V net or the total potential, electric potential, will be V1, that is the potential difference at point 1, plus electric potential at what, point 2, plus electric potential at point 3, plus electric potential at what, point 4. So let's go ahead and put in our value. Let's go ahead and put in our value. Let's go ahead and put in our value. So here, remember that V here is equals to KQ1, that's over R, then plus KQ2 over R plus KQ3 over R plus KQ4 over R. So let's look at that. Okay, sorry, KQ3 is going to be negative sign. Yeah, it's going to be what? Negative sign here. So it's going to be negative sign. So we have it as negative sign. So that is to say that this will cancel this. So we are now left with V net will now be equals to KQ over R plus KQ over R, which is equals to 2KQ over R. Now remember that our V net will now be equals to 2KQ over R. And what is our R? Our R is A divided by root 2. That is 2KQ divided by A root 2, which is now equals to 2KQ multiplied by root 2 over A. And the unit is what? Is the volts. This becomes the electric potential at the center of the square. At the center of the square. Okay, let's continue. So it says, find the point on the line AB where electric potential is 0. We have this point A here, okay, and we have a line. We have this is a positive charge to Q. So, and we have another charge here, negative Q, and this is point B, this point, and the distance between positive 2 and negative 1 here is what? Is 1 meter. So where on the line will the electric potential be 0? where on the line will electric potential be what? Be zero. Now, that means, look at this. This is positive what? 2. And this is negative what? 1. So this is a positive charge and this is what? A negative charge. There's going to be what? A force of attraction. So, but where on this line from A to B, where on this line will the electric potential be zero? So that means where will V equals to 0? Where are we going to place these charges so that the potential, electric potential, will be 0? Now, let us try to place at point, let us try to choose point P here. Let's try to choose point P here. Point P. That is between the two charges, positive charge and negative charge. So let's call the distance here from this to this. Let's call the distance, let's call it X. So if we call the distance X, that means the distance from positive 2 to P is not going to be 1 minus X, because the total distance is 1. Okay, the total distance is 1. All right. So let us now try to solve that. So let us now look at the potential. Let us now look at the potential at P. So the potential at P, that is Vp, will now be equals to the total potential, which is V1 plus what? V2. And they will be equals to 0, because it's asking us where the electric potential will be equals to. So we are choosing this point P to be where we are going to place it on the point, on the line, that the potential difference is going to be what? It's going to be 0. Now let's go ahead and look at that. So Vp will now be equals to potential at point 1. Potential at point 1 is going to be, remember our formula, is going to be what? K. Then here is going to be what? 2Q over the distance is what? Is 1 minus X. 1 minus X. Then plus the potential at point 2 is going to be K negative Q over the distance to point P is what? Is X. And it will be equals to 0. It will be equals to, so here Vp, let's cancel. We cancel this K. We cancel this Q. Then we also cancel this negative Q, and we cancel this Q too. We're now going to have 2 over 1 minus S is going to be equals to 1 over X. 1 over X. All right, so let's continue from here. So we are now going to have 2x will now be equals to 1 minus x by cross multiplying here. So we now have 2x plus x. trying to bring this over will be equals to 1. So we now have 3x is equals to 1. Then x is now equals to 1 over 3. So which is equals to 0.33 meter. So that means we are going to place this charge at point 0.33 meter, okay, between positive 2q and negative what q. For there to be no electric potential, for it to be 0. Okay, so let's go ahead and look at the second case, how we can also, where we can also place it that the potential, electric potential will be what? Will be 0. Let's look at that. Okay, let's look at case 2. Let's look at case 2. Then we also have this. Let's look at this also. We have also have, let's redraw our line. This is a positive 2q, and this is our negative q. We know that the distance here is 1 meter. And we have this point B. So we may decide to choose a point. We start to choose a point after this negative charge Q. We can choose a point here and we can call it W. We can call it what? W. So, and we have the distance from this negative charge to this point W. We can call it what? X. That is to say, the distance from positive 2 charge down to this W will be 1 plus x. Will be 1 plus x. Will be 1 plus x. So will be 1 plus x. Now let's also look at that. So the potential at W equals to potential at 1 plus potential at 2, which is equals to 0. Which is equals to 0. So let's now look at that. Potential at W will now be equals to potential at 1 is going to be what? K 2q over the distance is what? 1 plus x. Then plus the potential at 2 is going to be K negative q all over x, and it will be equals to 0. It will be equals to 0. It will be equals to 0. Now, potential at W is now going to be equals to K2q all over 1 plus x, also equals to kq all over x. Because here we have a negative sign here, so we introduce a positive sign. So it's not going to be, we can continue from up. So it's not to be, so V W will now be equals to, we cancel K, cancel Q, cancel K, cancel Q. It's not going to be 2 over 1 plus x is equals to 1 over x. We cross multiply, we have 2x is equal to 2x is equal to 1 plus x. So 2x minus x is now equals to 1. So we now have it that x is equals to 1 meter. So that is another point that you place the charge in order to have zero electric potential. Okay, now let's look at question number 5. An electron moves between plates A and B and gets kinetic energy from A to B and gets kinetic energy of 6.6 times 10 to the power negative 6 joules. Find the potential difference of the plates. So we have our kinetic energy is equals to 6.6 times 10 raised to power negative 16 joules, which is also equals to the work done. Also equals to the work done. Then find the potential difference. So we're looking at the potential difference of the plates. And we are looking at electron. The charge of electron is 1.6. That's negative 1.6 times 10 raised to power negative 19 coulombs. So remember that for the potential difference, we have it as potential difference is equals to AE over, that's charge of the electron, which is equals to 6.6 times 10 to the power negative 16 divided by the charge of electron is negative 1.6 times 10 raised to power 19. But here we are not considering the sign of the electron. So which is going to give us 4,125 joules per coulomb, or 4.1 times 10 raised to power 3 joule per coulomb. Or you can still keep the answer in what? In volts. You can keep the answer in volts. Okay, that is it for today. We are going to continue in the next class. So please don't forget to subscribe and share with your friends. See you in the next class. Thank you.